Hi, and welcome to May of 2018. And today on ATP, we're going to talk about CAN bus. Cool, CAN bus. Anybody hear about CAN bus? The thing that goes in all the cars, man. Yeah, we're going to talk about all that stuff. So let's go to the board. So CAN bus. What does CAN stand for? CAN stands for Controller Area Network. It is a differential signaling setup that runs on 120 ohm twisted pair, just like RS-485. It does framing, error detection, and some amount of flow control, like a UART. It is multi-master, it is message-based, which is really cool. We'll talk about it as we go. And it is a prioritized addressing scheme that is sort of wrapped around the message. And it has this really slick method of collision control on the bus. And when you follow all the rules of setting up the network, you can get as much as 1 megabit per second at a distance of 40 meters. Now let's talk about some history. When you hear the words CAN bus, you probably think, oh, that's the bus that's in all the cars and trucks and stuff. Yeah, OBD2. Well, yes, but qualified, and I want to try to spell that out really carefully. But some history. Bosch did the original development of the CAN bus standard in the mid-1980s, and the whole point behind it was that cars were getting more complicated, right? We wanted all of our gear to work really well. We had switches to do everything and do remote things, and I'm in my luxury ride, right? Well, there's a lot of complicated wiring that goes behind that. Like, you know, you've got switches on your hand here that control the windows in the back so your kids can't climb out. And so that ends up being a lot of wiring everywhere. And so what they wanted to do was they wanted to make a system where you could just put like a microcontroller into a device, and you had a universal bus that you could just dump data onto, and the message would get to where it needs to go without the need of all the excessive copper in the system, right? So that's where CAN bus actually came from. First car with CAN technology came out in 1991. It was a Mercedes W140. Also in 1991, Bosch releases a couple of more specs, CAN 2.0, A and B. Now, we'll get deeper into that, but just as a quick explanation, 2.0A has an 11-bit address field, and I'll detail all of this. 2.0B has a 29-bit address field, so we'll talk about that. And OBD2 became a mandatory part of US car manufacturing in 1996. Now let's talk a little deeper about the structure of CAN and its relationship to OBD2. So let's talk about CAN bus and OBD2 and how they relate to each other. CAN bus is a subset of what happens under the heading of OBD2. OBD2 stands for Onboard Diagnostics, and it is the diagnostic system that runs on your car, runs on lots and lots of vehicles. But CAN bus is only one of several physical mediums through which OBD2 functions, okay? So when you think, yeah, CAN bus is in the cars and OBD2, yes, but. So I just want you to understand what that distinction is. This being the OSI model of network gobbledygook. CAN bus covers the physical layer and the data link layer, where OBD2 is actually up here, but it kind of encompasses that with the other buses. So you get what I'm talking about. Now, with regard to CAN bus, there are lots of documents, but the ones that govern the spec that you can most likely point to easily are going to be ISO, the International Organization for Standardization. I love trying to remember that all the time. ISO 11898-1, -2, and -3. These are the primary ones. All right. Now, there's also, well, let me just describe these first. -1 deals with the data link. And I have read some of these documents, although they aren't official ISO documents, because if you go to their website, they expect you to pay money for the information. I hate paying money for information. It's a crime. But I'm not going to be able to point to official documents. I searched for the numbers, came up with sketchy websites that had something that said ISO on it with the number, so I read it. And I read it in a few different locations, so I'm thinking I probably got it. Dash 1 deals with the data link layer, which is a lot of networking awfulness for you people who like that sort of thing. You guys are freaky. Anyway, Dash 2 deals with high-speed CAN. Dash 3 deals with low-speed fault-tolerant CAN. And when you dig into these, it is literally just the structure of the bus, the terminations of the bus, the lengths of the stubs, yada, yada, yada. And we'll talk about that as we go. Now, like I said, there's also a Dash 4, a Dash 5, and a Dash 6. 1198-4, 11898-4 deals with time-triggered communication. Dash 5 is an extension of 2, the high-speed CAN, which deals with low power. And Dash 6 is a further extension of that, which deals with selective wake-up. But we're not going to focus there. We're going to focus on the big 3. All right? Anything on this screen I haven't covered? I think we're good to continue. So what does the bus actually look like? Well, let's start with the high-speed variation, which is 11898-2. And it looks a lot like what, if you saw the last video, it looks a lot like what an RS-485 bus looks like. It is linear, again, this is the high-speed variation, linear, twisted pair, terminated at either end of the linear bus with 120 ohm resistors, okay? The nodes, the individual nodes, do not have termination resistors on them. But the spec specifies that each stub length, right, the distance between a node and the bus is no greater than 30 centimeters. Now, caveat, that's a rule of thumb that will generally get you where you want to go if you follow the rules. If you want to get sticky about it, you can actually calculate what the length is given transition time of your node, your farthest node from the end, versus the length and the time it takes to transit, right? They're watching for the edges. They want to make sure you don't get a reflection down one end to the other that jacks with your edges. And as long as you keep these things less than 30 centimeters, you're probably going to be good to go. All right, so you follow that, you get 1 megabit up to 40 meters, probably. Now let's look at the other one. Okay, so for the other bus, low speed, fault tolerant, which is detailed in ISO 11898-3. The gist of this bus structure is not at all like the linear bus. Now, if you read the ISO document, if you manage to pay for that or find one of the bootleg copies, or you look at Wikipedia, they try to suggest like, well, we kind of want it linear, but you can do all this other junk too. I ain't just gonna do this other junk. So basically, the gist of this is that instead of terminating either end of a linear bus with 120 ohms, you terminate at the nodes themselves, and you can do all kinds of wacky stuff. Now, the terminations, and I have this drawn a little bit goofy, but one of them, CAN low, is pulled to 5 volts. CAN high is pulled to ground. And the reason they do that is because when the bus or when any given transceiver is asserting a recessive bit, they want it to go to the recessive bit by passive means, right? They only drive the bus when it is asserting a dominant bit. And as we look at the data, it'll sort of become clear. Now, let's see. So node, pulled high, pulled low, you can do all kinds of junk. Now, the termination resistance, they want the overall termination resistance to be around 100 ohms, but they don't want any one resistor to be less than 500. And if you read the spec, it says, quote, due to semiconductor manufacturers' constraints. I don't exactly know what that means. I can imagine some things, but I'll leave that for y'all to speculate. So that's the termination condition. Now, if you follow those rules, you can expect a data rate between 40K to 125K. So for a non-critical system that you have a little time to play with, that's pretty okay. Now, while we're here, and right before we start getting into what the data structure looks like, the signal and the data frame, I will mention that each of these nodes is actually comprised of a CAN transceiver, and a CAN controller, and then there's like application stuff sitting in code on top of that. The CAN transceivers are usually in the neighborhood of $1 if you buy them separately. A CAN controller is like between $1 and $2, depending on feature set that you're looking for. And you can buy some that are completely integrated for assumably more money. And we'll talk about the features in a bit, right? There's always like some things that I'm always like, where do I put this in? I'll put stuff in, don't worry. All right, so let's move on. Okay, now, what the data looks like on the bus. If you were just to plug into the bus with a scope and look at it, this is sort of what you would see. In the case of high speed, 11898-2, your two signals, CAN high and CAN low, 0 volts, 5 volts, that's what we're looking at. 0 is represented when CAN high is driven high and CAN low is driven low. That's a 0, that is the dominant state, okay? Recessive, the transceiver stops actively driving the bus and the lines return to, remember the 120 ohm resistor? They return to somewhere in the middle, right around 2.5 volts. But because there is no bias network outside of that 120 ohm resistor, these two things in the recessive state are very, very close together. There's only 120 ohms separating them. So if there's no current flow, the voltages are the same. So, in the case of low speed, which is 11898-3, you have a greater separation. Remember that each of the lines, CAN high and CAN low, are held to VCC and ground. So by that logic, this is CAN high starting here, and this is CAN low starting there. And again, that's the dominant bit, that's the recessive bit. Now, a couple of things that you should probably be able to see right off the bat. There's a greater separation between on and off for the low speed, right? Greater separation, greater immunity to noise on the lines, right? Besides that it's a differential line and there's common mode rejection, yada, yada, yada. You can look at this and go, oh, okay, I get it. It'll take more noise to obstruct that. Not only that, but you can sort of see why there is a reduction in your data rate, because you've got a much greater transition you've got to account for. So it's necessarily slowing everything down. Let's see. Then there's this one thing that I keep wanting to mention, and I can't seem to find the right spot to say it, so I'm just going to say it right here. When the transceivers are active on the bus, they're always listening, right? The structure of the bus is such that each transceiver, each node, is always listening to all messages, and then they filter out the ones that they want and disregard the ones that they don't. Now, that's going to come into play as we describe in a little bit both arbitration and error flags and overload flags. And we'll get to that, but I wanted to mention at this point, the transceivers, the nodes, are always active. I mean, you can put them in standby, but generally they're anticipated to be always participating in bus traffic, okay? Next step. So, what the data actually looks like. I have represented here a couple of things overarching that I want to say before we do this. I have represented here CAN 2.0A, which is 11-bit identifier, and CAN 2.0B, which is 29-bit identifier. And I'm going to explain how this all works. Now, also at the top, I want to mention there are 4 different kinds of frames that they address. One is a data frame, one is a remote request frame, which is how one system asks another system for information. And then there is an error frame, and then there is an overload frame. And they sound very big and scary, but they're really not. So let's talk. Now, in 2.0A, what you have basically, and it's not too very complicated, you have a start bit, and then you have an ID field, which is 11 bits long, okay? And then you have the RTR bit, which is the remote transmit request. I think that's RTR. So if it's going to be a frame that's asking for data, that bit is going to be flipped, and we'll talk about how that all changes in a sec. Then there's the IDE bit, which is identifier extension, ID extension. So this bit gets set if it's 2.0B, 29-bit ID, okay? And just to finish out the 2.0A, after the ID extension bit, we have a reserved bit. I think the spec says it must be high, but it can be either. Okay, fine, whatever. Then there's the DLC field, which is data length code. It is 4 bits, and it says how much data is in the data field, which is 0 to 8 bytes. That's standard. Brief aside, there are some there are higher level bits that sit on top of CAN bus that allow you to send more than 8 bytes at a time. We're not talking about that today, just to mention it though. So 0 to 8 bytes. Then there is a CRC that is 15 bits, followed by a CRC delimiter, which is 1 bit, an acknowledge bit, followed by an acknowledge delimiter, and then an end of file, which is 7 bits long, all of them high, and then an interframe space, which is at least 3 bits long, okay? That's all in the spec. Now, 2.0B, what happens is that you're going along and, oh, the IDE bit is set. So then all the nodes know, okay, this is the 29-bit identifier. And so what happens is the RTR bit that happened just before that, the request to send data, that down here, SSR, they throw that one away apparently. And maybe somebody can check me on this, but it looks like that just becomes a filler. Like, oh, we're not paying attention to that anymore because we have an extended ID. So we have the ID bit after that, and then the additional 18 bits follows that. All the receivers know if that bit got set, this is more ID, okay? Then there's the actual request to send data. This is the bit now that we're looking at if we need to send data. So it all changed. Followed by 2 more reserved bits, again, same game as the previous one. The spec will say something like, it must be high, but we'll take it in whatever you send it. Okay, fine. Followed by the data length code, again, 0 to 8 bits, CRC, acknowledge, end of file, and interframe space. So let's talk about bit stuffing. Something about the CAN transceiver that you ought to know is that while it's considered an asynchronous signal, I mean, synchronicity is obviously a very big part of making any bus work. Now, the way that is maintained is that the transceiver, each transceiver will actually sync on every transition from a recessive bit to a dominant bit. I need to double check that. I just look at my notes to dominant. Recessive to dominant bit. It'll sync on every transition from a recessive to dominant bit, and it starts at the start bit. When that sucker goes low, starts timing, okay? And on every transition that it sees from recessive to dominant, it's going to resync. And the way it does that, right, it splits the bits into quantized sections. And if a transition doesn't occur where the transceiver expects it to occur, it will augment its bit timing. And so it will continuously try to keep in sync with what it's hearing, okay? Now, in order for that to work, they don't want to see more than 5 consecutive bits being any one polarity. And so what they will do is if they've got a long string of one value, at the end of the 5th, they'll throw one in just so we can resync, okay? That's called bit stuffing. Now, the receiving device is counting the bits, right? That's why being synchronous is a lot of reasons why it's important. But it will see 5 in a row and go, okay, the next one is a stuffed bit. And the receiver will pull that out, okay? Now, bit stuffing becomes very important for things like error checking, error control. In fact, I'm going to talk about the error frame next. Let's talk about error frames and overload frames. Now, remember going into this that all of the transceivers are participating hopefully, ideally, in bus traffic, right? And so they're all, everybody's playing the game. Now, what an error frame is that when any given node hears something that's either a receive error or a transmit error, what it will do is it will start transmitting what is called an error frame. And what it is 6 dominant bits followed by 8 recessive bits followed by the inner frame spacing, the 3 bits there, okay? Why 6? Well, we just talked about bit stuffing, right? We don't want more than 5 consecutive bits of any one value. If we find that, it's an error. Okay, so whenever there is an error on the bus that any of the nodes detects, each node that detects it will shout out this error frame, okay? Each one of the receivers actually has error counters in it, okay? They are counting transmit errors and they are counting receive errors. And they go from 0 to 255. So what happens with the counters, if both of the counters are less than 128, if less than 128 transmit and receive errors have occurred, the device will transmit an active error frame, which is to say that it is going to send 6 dominant bits followed by 8 recessive bits, yada, yada, yada. If either one of those counters is greater than or equal to 128 and less than 256, it will transmit passive bits. I hate this. What it actually means is it's not doing anything. It's not sending anything. It's just sitting there for this much time. So it'll sit passive for 6 bits, and then 8 bits, and then 3 bits of interframe spacing. And then if the transmit counter gets over 255, it'll just stop. It's like, okay, sit down and shut up. All right, so let's review that again. If any error happens on the bus, every one of the nodes is gonna be like, bop, 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 bop. That was an error, and it'll start sending out bits, okay? Now, 6 bits, because everybody's gonna see it as an error. And so practically what you see on the bus is like, you know, there'll be one device that sees the error and it'll start going, and then all the other devices will be like, yep, that was an error. And so you'll get this smearing of error frames, and then by the time the last one goes, there's still like the 3 bits, yada, yada, yada. So that is error frame and the error counters and how those work. Overload frame. An error frame will only happen during the course of a data frame. It'll happen in the middle. It could be like a remote frame or a data frame, but it will happen in the middle of the frame, okay? And it always happens when there is an error on the bus in some fashion. Now, an overload frame takes the general shape of the error frame, which is still 6 bits dominant followed by 8 bits recessive. But this guy only happens in between frames. It happens during the IFS, okay? And the whole reason that happens is because there's somebody on the bus that can't get their stuff together and they need more time. And so the offending unit will spit out this overload frame, and it will cause everybody else to go, okay, whatever, and it will wait, okay? So the last thing I want to talk about is arbitration. And this is a really cool aspect of CAN bus, in that you can have just 2 wires and a whole bunch of different nodes that are trying to communicate, and they can get data across, and the arbitration method is such that you don't lose any data. You don't have a collision and then everybody's trying to pick up the pieces like, what was that? I don't know. So have this drawn out. So for example, I've got 3 nodes here. We'll call that the start bit. There's the start bit. Now, as you recall, every one of the nodes is listening. And not only are they listening to what's being transmitted on the bus by others, they're listening back to what they're saying. And that's how this works. So the start bit, everybody's happy and they're checking like, okay, everything's cool. On the very next bit, the way I've got it drawn, I've got node 3 goes high while nodes 2 and 1 are still held low. Now, node 3 is going to listen to this and go, okay, I'm transmitting a 1 now, and it's going to listen and go, oh, that's not a 1. Geez, I got to get off the bus and let somebody else go. So node 3 drops out at that point. It is no longer transmitting, and the others go happily along. And node 1 gets down to a couple more bits of zeros, and then it goes to a 1, and it listens back and it goes, oh, 0, that's not what I sent. All right, I'll shut up too. And then node 2 happily goes on and it finishes its business, unless there are other nodes, right? Now, this is assuming, worst case scenario, that there are going to be nodes stomping on each other in a very synchronous fashion like this. Well, the fact of the matter is, any given node is going to be listening for something. Before it starts transmitting, it checks the bus and goes, are we free? Yeah, okay. So if it just so happens that you get this sort of thing, this is how it will play out. And that's a really cool thing about CAN bus. Now I'm going to talk about a little more of the hierarchy and how we're going to move forward with this. All right, we're very close to where we're going to break today. But you see what I have written down here. Practical communication. Now, everything I've given you so far is a description of the low-level functionality of what happens in CAN bus. But I haven't told you how to actually talk over a CAN bus. And that gets more complicated. Now, the hierarchy of, well, that was fun. The hierarchy of what CAN bus sort of looks like at higher and higher networking levels is that you've got message objects, and there's like a list of attributes, right? The message has an address, which is something, and then it's got attributes that are associated with that address. And at a high level, you can set up the message objects with data you want to send or data you want to receive, and you can just address that message object from inside of your microcontroller through your application, okay? And much of it is highly automated. You can set, right, the functionality of the CAN bus, and depending on the parts that you choose, can make it a very highly automated process where you're not loading a part into a register or a number in a register and send. You can do it that way, but the higher and higher networking levels allow you to abstract out a lot of that stuff. And I will tell you that at a very low level, like in the microcontroller, you are going to be setting up registers, you're going to be flipping bits. It's a lot like a UART. If you've ever set up a UART from scratch inside of a micro, you know that there are a lot of things you gotta set, and you gotta set them in just the right order a lot of times, or it will not function. So CAN bus at that level, yet at the data link level, is kind of a bear to set up. You can do it, but it's a pain. Now in our case, right now we've got the CAN 485 board, and I've been through their example files, and they're pretty straightforward, where you're actually setting up the data fields independently and sending a message, okay? So that takes a lot of the abstraction out for you. But like I say, setting it up at a low level is difficult, and that's why we have things like CAN Open and other applications that sit on top of CAN bus that make it easier, right? They set up all that stuff with your microcontroller. Now, that leaves me at this point right here where I really want to say, oh, this is how you send stuff on a CAN bus. But the fact of the matter is, all of this stuff that you set up is going to be highly dependent on the components that you choose, right? Every CAN controller has a different set of features that will allow you to do different things. Some are very elaborate, some have libraries written for them, some of them are really bare bones, okay? So I can't get too terribly in depth here. But I want to carry this forward, and the way I want to carry it forward is I want to talk about OBD2 next, right? If you're setting up a CAN bus on your own, you've got your own network, you've got your own topology, and you're doing this from scratch, you've got a very good chance of being successful with the tools that are available, right? The CAN 485 board is awesome, and the libraries that are available make it really stinking easy. But if you're gonna try to get into something where there's an existing CAN bus, an existing command structure like OBD2, that's more complicated. But I get the impression that a lot of people who are watching this video are like, CAN bus, OBD2, yes, let's go. But it's not the same. But next video, and I promise this, I've only got 3 weeks to do this, I'm going to dig into OBD2, talk about its relationship to CAN bus again, talk about the other buses that are on it, how do you attach to it, yada, yada, yada. And I'll see if I can get some data out of my car, which is like a 2015 Volkswagen GTI, and it's still under warranty, so I'm a little iffy about this. So thanks for coming and checking out SparkFun and According to Pete this May of 2018. I hope you enjoyed CAN bus. I hope you learned some stuff. I learned a bunch doing this. It was really fun. And next time, OBD2 on a car under warranty. See you next time. Bye! It's April. No, it's May. It's May. It's May. Welcome to May of brain fart. Data request frame. What's the right? Maybe stupid isn't the right word. No, stupid is the right word. CAN bus, and we're afraid to add. I'm just like, it's falling apart as I say the words. Damn it! I can't remember what the actual term is. Hang on. And I just lost my train of thought. God. Damn. I was gonna say something, and then I was like, wait, no, say this. And then it all went blank, and I'm staring at a blank board in my head. This is terrible. This is just terrible. I gotta do this again. Disregard all of that. 0, did I do that right? I've got this backwards. Stop.